Hello, my friends. This is Dr. Dixon K. Chembe. I'm going to take you through working on starting DC motors. This course um, is a very good course for those that are for technicians, for artisans, and those that are working in industry, even for engineers, because you need to understand how to start a direct current motor. Is different from the way we start AC motors, because for AC motors it's easy for us to stop the AC motors because we've got the sine wave, and we can easily stop AC motors. Otherwise, if we are to run, start and stop DC motors, we run into issues of arcing. Arcing is where there's the contactor refuses to open, or it opens but there's a current that connects between one contact to the other, creating an arc. And that arcing is caused because you've got direct current, it's not alternating, and it's difficult to cut it. So you have to segment the contactors. There are special contactors that are used to operate DC motors. In the meantime, we've got circuits that we are going to look at, circuits that are going to uh, explain, um, in which we are going to explain how to start DC motors. There are several types of DC motors. First of all, you have to understand that. The first thing that we need to sort out is what kind of DC starters that we have. Okay, so first of all, the three basic types of DC starters, or three basic types of DC motors, sorry, that exist. We've got the series motor, which you see here. This is a series motor where you have the armature in series with the coil, the series coil. And then we've got the shunt motor, where you see the shunt field, which is labeled F1 and F2, connected across the armature. This shunts the armature, no wonder it is called a shunt motor. And thirdly, we've got a compound motor, which is a combination of all of the series motor as well as the shunt motor. And this each type of motor has got special advantages. For instance, the series motor does give high starting torques, but it's very difficult to regulate its speed. Whereas the shunt motor is easier for speed regulation applications. It works out very well. And also the compound motor is good for speed regulation applications. As we see, this is the motor, DC motor. You've got the brushes there connected, the commutator, which I'm sure if you've done electrical machines principles, you have covered. So we're not going to dwell deep into explaining what really a DC motor and components of a DC motor. But you have to notice that the rotor here is wound, similar to wound rotor machines or synchronous machines. These are the essential parts of a DC motor. We'll not dwell deep in that, but we want to analyze the parts of that motor. So the rotating part in a DC motor is called the armature, constructed with slots for windings. So what we call the armature is essentially a combination of the commutator and the windings. It forms the armature. And for the field windings, we've got two types of field windings. We've got the series field, which you've seen in the slides as terminals S1 and S2 connected in series with the armature. It has low resistance, whereas the shunt field which you've seen as F1 and F2 connected in parallel with the armature, has got high resistance. The commutator is a mechanical switch that forces the current to flow through the armature windings in the same direction. Essentially, what you don't want is for the motor to be reversing every once in a while. So the commutator ensures that as the current changes direction, it is maintained to flow in the same direction and does not switch, and therefore does not reverse the motor. To reverse the direction of the rotating or rotation of a DC motor, one simply has to change the position of the terminals of the armature. This is done by reversing. If you can see on top here, the motor is running in counterclockwise direction. So you've got A1 and A2 terminals on the armature, which when you reverse, you've got A1 coming to this side and A2 going to the other side. Then you reverse the direction of a DC motor. You can also do that by reversing the field. In a similar way, you reverse the field terminals, which is S1 and S2. Once these are reversed, you reverse the direction of a DC motor. I hope you do know that for AC motors, three-phase AC motors, we reverse the direction of flow by changing two of the phases. We change the two of the phases, and in that way we reverse the direction of AC motors. For single-phase AC motors, we simply change the terminals. So the terminals that we have are reversed to interchanged, and you change the direction of operation of the motor. For a compound motor, it's the same application. We simply, as you can see, we've reversed the terminals of the armature. A1 has been turned to the right side, the other side, and A2 to the other side. That reverses the direction of rotation of the compound DC motor. Now, talking about motor starters, there are two main kinds of motor starters that exist. One is the current limit acceleration, which simply uses acceleration relays to limit the acceleration of the motor, and in turn limit the inrush current. All motor starters, the basic principle is to limit the starting inrush current, because if the inrush current is very high, then you are going to experience motors burning, and you want to avoid that, especially for big motors. For smaller motors up to a level of 5 horsepower, we can use direct online, meaning we do not need to include a starter to work on that motor. Simply by connecting it direct online, you can run a small DC motor. Whereas for large DC motors, we need to control that high inrush current. And in this way, we look at the two types of starters for DC motors, which are the current limit acceleration and this definite time acceleration. So the current limit starters are further split into three types. You've got the series relay type, the counter EMF type, and the lockout type. So all these three starters use acceleration relays, special relays that are implemented in the DC control circuit to run. The first circuit we are going to analyze is a series relay, a current limit starter. So as you can see, the series relay has three acceleration relays, 1 AR, 2 AR, and 3 AR connected in series with the armature. So as current flows through this circuit, the acceleration relay will be connected in series with the armature. Again, there are 4 contactors that are connected in this circuit. You've got the main contactor, which is a motor contactor, the contactor 1A, contactor 2A, and contactor 3A. Sorry about my roster. My roster's timed, so is making some noises there. I hope you can ignore his noises. Okay, so let's go through the circuit. So what we have here is we're going to follow the circuit. I'm gonna bring on my sketch pad to show you what I'm talking about properly. Okay, so here I'll use a pencil to guide you with the flow of current. Okay, so sorry about that. So as we start the start button, so we push the start button here. The start button is going to allow the current to flow from that direction through to the main contactor M. When M is energized, it is going to close all its normally open contacts, which is this contact is going to close, this contact is going to close, that contact is going to close, allowing connection of the of all the contactors in the circuit. So what is going to happen is initially the current will flow through the 1AR, which is an acceleration relay, through resistor 1, resistor 2, resistor 3, interpole field, and through to the armature. So this means that the motor has started running with the first acceleration relay in series. Okay, so the acceleration relay is going to be activated, is going to pick up what we call pickup once the inrush current flows through, high inrush current flows through 1AR. That high inrush current makes the acceleration relay to pick up. After it picks up, it's going to open this contact. So that opens, ensuring that contactor 1A does not energize. So this remains open, and once the motor speeds up, we are going to experience the acceleration, the inrush current dropping. As the inrush current drops, the acceleration relay A1AR is going to drop out, meaning it's going to de-energize. Okay, when it de-energizes or drops out, it's going to retain its contact. So 1AR retains to its normal status, which is closed. So this contact, which was open, closes back, bringing on 1AR to energize. Once 1AR gets energized, it closes, 1A gets energized, it closes its auxiliary contact 1A. Once this is closed, the secondary inrush current is going to flow through 2AR, through resistor 2, resistor 3, and to the armature. So this ensures that resistor 1 is short-circuited out of the circuit. Again, this second inrush current that comes is going to make 2AR to pick up. Once 2AR picks up, it's going to take to ensure that 2AR auxiliary contact here opens up. So this is going to open up, while when 1A was activated or energized, it closed its auxiliary contact there. So this is closed and this is open. This ensures that always in most cases 2AR does not energize. After the motor gains speed, we're going to experience a similar behavior. So the inrush current is going to drop, which is going to ensure that our 2AR here drops out. Once 2AR drops out, it's going to retain its contact here to its normal status, to a closed status. So 2AR auxiliary contact closes back. You remember 1A is already closed, so current flows to energize contactor 2A, which in turn closes all its auxiliary contacts. So in this case, we've got auxiliary contact here closing. Once 2A closes, a third inrush current is going to flow through 3AR, resistor 3, interpole field, and armature. This ensures that resistor 1 and 2 are short-circuited out of the circuit. Okay? And as 2A gets energized here, it's going to close its normally open auxiliary contact 2A. And 3AR is open as the acceleration relay 3A picks up. Again, the motor is going to increase speed. As it increases speed, we're going to experience 3AR dropping out. Once 3AR drops out, it's going to retain this to its normally closed status. So 3AR closes back, and you remember once 2A was energized, it closed that contact, so allowing current to flow through to 3A. Once 3A contactor is energized, it's going to close its auxiliary contact there, and we have now the current passing through the circuit through the auxiliary contacts 1A, 2A, 3A, and bypassing all the three resistances to the armature. So in that way, the motor has attained its full speed, and all the three resistances, resistor 1, 2, 3, have been short-circuited out. Okay, so that's the way this circuit operates. I hope you followed. And